Hello my dear students, we are back with a new chapter now, that is integration, class 12 mathematics chapter 7. Considered generally assumed, I would say, assumed as a very difficult, something like that, difficult chapter of class 12 mathematics, which I would say not so. Of course it is difficult, it's not going to be that easy, but not impossible, I would rather say that. Okay, but that depends on the person concerned, that depends on the learner. If you're interested, enthusiastic, determined, then of course with practice, absolutely not difficult at all. It's easy, just about the concept, and of course mathematics, we all say it's all about practice. So if you can just understand the way how it works, then of course it's slightly more, I would say, slightly more complicated with respect to differentiation, but it's kind of interesting also, because the more challenging the things are, definitely the more interesting it is, isn't it? So challenging things makes us better in life. So if you remember differentiation, we have already done how it was related, with slope, tangents, and so on. So actually integration is just a reverse process of differentiation. Okay, it's just a reverse process of differentiation. So all the formulas are just going to be now reverse. That's why of course it's called antiderivative also. It is also known as antiderivative, or in other words, reverse process of differentiation, which means that all the formulas that we had in differentiation are just going to be reversed. So that's when it becomes confusing for students, like all the derivatives, so many formulas, differentiation, derivatives and all. In integration, most of those formulas just reverses, as it says, antiderivative, a reverse process of differentiation. But again, as I said, with practice, it's going to be easy. I'm there to help you out as much as I can from whatever I know. So definitely let's work together. So yeah, you can, of course, this is going to be just an introduction class, so I'll make it very brief as much as possible. Just get the general concept. Okay, that's what this integration is all about. From the next video, definitely we're moving straight to the formulas, the mathematical part and all. No, this is not physics, so definitely we're not going to be really much interested in that physical part and all. No? We're just going to be interested in the mathematical part. Okay, right. So as I mentioned here, integration is nothing but the antiderivative, or the reverse process of differentiation. So if you remember, in differentiation, what did we do? Differentiation we did, as we were discussing, slope of tangents. Generally instantaneous rate of change. So generally in differentiation, what happens is we talk about small things, isn't it? Small parts. No, instantaneous rate of change. Integration basically is about the complete. Differentiation, small part. Integration, the complete part. We can just sum that as area, the complete part. So that's how it differs. That's why it's a reverse process. Small, big, complete. No, small part, the full part. Okay, so like differentiation, derivative, you can note down these small terms also. Okay, very important. Derivative of a function. Derivative of a function, how is it different from integration? Integration of a function. So in derivative of a function, what we talk about instantaneous rate of change. Just one of the examples, instantaneous, instantaneous rate of change. Instantaneous rate of change. Integration generally talks about area under its curve. Okay, area under its curve. It's also of course used to find a function when its derivative is given. That's why it's called the reverse process of differentiation, function, derivative. So we can use that derivative to get the function again. No, that means we can just go back and get the function from where the derivative came. That's why it's called antiderivative, anti-missile, no? Anti-missile. So that's what we are going to learn here. So basically now integration, how I would tell is like it's generally used to find out the area. More commonly used, there are many other uses also. So more commonly used to find out the area under a particular curve. Now for example, let's take one example. Suppose, let's say this. This is just a conceptual topic to be discussed in this particular video. So just try to understand, grasp the concept, so that next time it's going to be like, from the next video it's going to be easier for us. Like for example, there is a curve in this form, maybe up to here, from 0 to A. So what is the area under this curve? That's going to be quite easy, because the area under this straight line, under this curve, is in the form of a rectangle, so length into breadth, so that's no problem because it's a solid figure with a proper shape, so we can find out the area under its curve. But not every time the situation is going to be so ideal and so perfect, isn't it? Absolutely not. No. So because for example, like velocity of a particle, velocity of an object. So when an object moves, what happens? It moves at variable speed or variable velocity in terms of magnitude. Variable speed, it rises. See, if I move from here to, let's say, one point, and then I say that in 2 hours my average velocity was 30 kilometers per hour. It doesn't mean that throughout the whole journey I was traveling with 30 kilometers fixed. No, definitely there were times when I put on the brake, when I stopped for a tea, maybe a small cup of tea. So it varies. Sometimes it goes up to 50-60 kilometers per hour. Sometimes it goes down to 0, because 60 plus 0 divided by 2, that's again 30, isn't it? So maybe our curve is something like this, till we come to the last point, final point, maybe from 0 to that point A. This is maybe the variable with time. This is the velocity time. Now if I tell you, find out the area under this curve, how are you going to do it? If I tell you to find out the area under this curve, how are we going to do it? Now that's a question, isn't it? That's a question, and that's where integration comes into play. It helps us find out this real day-to-day life associated problems, area under the curve. How do we find out? Now what I'm going to do here is this graph, I'm going to break it into smaller rectangular parts, something like this. For example, I'll start with the easiest one, this part. Now this is one smaller rectangular part, so this area I can easily find out, isn't it? That's not a big problem, right? Because it's just going to be length into breadth, so that's done. Similarly, I'm going to cut this into smaller parts. So if I can just cut it into smaller rectangular parts, the whole entire area, the smaller rectangular parts, then it will be, of course, easy for me to find out small rectangular parts. So I'll just consider this as the length, and breadth, and this as the length. You may be having some doubts, but don't worry, I'll come back to that point also. So some brilliant students might be thinking, what about don't worry, I'll talk about that. So if we can just cut it into small rectangular parts, and then maybe just get the total of it, get the sum of it, then definitely I will be able to get the area under the curve. Not a big problem, isn't it? So that's why, in other words, let's say I cut it into small parts like delta x parts. Okay, each part is delta x. So summation of the small parts, summation of all the small parts, the total of all the small parts will definitely give me the areas. Simple as that, isn't it? So with respect to velocity, the velocity function along t, right, along t, velocity function, area under the graph of the velocity curve along t. If I can just add all the small parts into dt means all the small parts that I have, dt or delta t, or I'll just write dt. So if I just add all the small parts, definitely I will be able to find out the area under the curve. Got it? A simple concept, isn't it? So I should be writing something like this, summation, right? Because it's the total, but we don't do that. We don't write this summation. Instead of this summation, what we do is, for questions like this, conditions like this, we use this, a curved, something like an S figure, which is called the integral. Okay, we use this integration sign. Now some of us may ask, then why don't we write summation simply, because it's just addition, so why don't we just write summation? Why do we have to write this, this new symbol and all? Now the reason is this. But of course, I hope you got the concept, isn't it? Simple concept there. See, this is a very huge topic, okay? Very huge topic. There are many more applications of integration, but I'm just discussing one general concept, application of integration, which will be there in chapter 8 also, again, this application of integrals, area under the curve. So that's why based on that, I'm just giving you one application on how integration can be applied in our day-to-day life. Now, I hope you have understood the concept, no? Area under the curve, we cut it into small rectangular parts, we add them up, that's how we get the area. Simple concept, but we do not write summation. Question is, why don't we write this summation sign? Why do we have to write this new symbol, integration? Problem is this. When we were cutting this into smaller parts, what happened is, okay, this side we can assume to be the breadth, no problem, but this side, see this small curve, this is actually not the length, because if I just draw the rectangular, then this small part is actually what? Neglected, isn't it? So somehow summation, so all these parts from all these curves are left out. Maybe only here exact rectangle might come, something like this. All these parts are left out, which cannot happen because it's area under the curve, and that is the reason why we don't write this summation, because summation means just add them up. So if we just do that, we are ignoring all these parts. But integration takes care of that. Okay, why? That's the reason why we write this integration sign, this sign. Okay, it takes care of that. How? I'll tell you. Why do we write this notation is because, see, one problem that we can, how can we avoid this particular problem? That problem will be avoided by taking this interval as small as possible. As small as possible, because the bigger it is, see, even here also, if I take it very, very small, very small, very, very small, then this will not make much difference, because a small curve, a very small curve, will definitely look like a straight line. So that's not going to be much of a problem for us if we can make the intervals more and more smaller. So that's what integration is talking about actually. Okay, we get the area of a curve by summing up all the intervals. Condition is that the intervals, these intervals should be very, very small. That's what it is trying to say. So that's why instead of this summation, what do we do is we write this integration sign. What does this integration sign mean? It means that it is telling us that, hey, listen, make sure that the interval that you're using to find out the area of the curve, that interval is as small as possibly you can take. Got that? And that is the reason why we use this integration sign. So let's not create a big issue about this integration. Simple concept, bus. That's it. Okay. Now, I'll give you some pointers about this integration. That is, of course, as I say, many more applications. I'm just giving you one example based on that. Alright, so suppose, let's say, a function is given to us. So how do we write down the derivative of a function? Derivative of a function with respect to the variable t is, that's the way we write it, isn't it? So how do we write down the integral of a function? Integral of a function will be this function with respect to t. That is, in other words, in simple words, what do we do is the function, the area under the curve, the function is added actually how many times? dt times into dt, smaller parts into, so we are adding them up along t. Along t. That's what it means. So we're integration of a function with respect to t, that is along this direction. We're adding all the small parts dt into t. That's why we say multiply. That's what is derivative is all about. Derivative is like small parts, so it's something like dividing, cutting it into smaller parts. Integration is like multiplying, we add them up. That's why it's called integration of a function with respect to that particular variable. Alright, that particular variable. Now, and I hope you've got that. Of course, you can just write maybe like, of course, I hope you have understood the concept between why don't we write this summation. I don't have to give you, I guess, summation and. Why don't we write this summation and instead of this summation, why do we write this integral? Because Remember, intervals should be as small as possible. Alright, so let me just write it down. That is, you can also note it down, that is sum, that is area, according to that particular example that I have given you, that is area of the rectangles, RECTANGLES. Okay, sum, that is the areas of the rectangles, actually will give us the total area under the curve, provided that, I'll just write delta x, okay, provided that delta x tends to 0, delta x or delta t or whatever will be that interval I mean, okay, as delta x tends to 0, and that's what integration, that sign is all about, not summation. Alright, now that means, now since it's a reverse process of integration, differentiation, that's going to be, if we have a function f of t, then its derivative, then its derivative will give me f dash of t. Simple as that. Then in that case, its reverse process, if we go reverse, that is anti-derivative of f dash of t, that is anti-derivative of f dash of t will be f dash of t with respect to t. So that will give me the function back. So that's why I was telling you one point, that this integration can also be used to find out the function whose derivative is given to us. The function whose derivative is given to us, we can get the function of that function whose derivative is given to us. That's why it's called antiderivative. Okay, alright, so I hope you've just quickly, roughly written it down for your convenience. Now, let me give you another small hint. Note, that is, you can just note down this, that is derivative of a function. Derivative, let's say derivative of a function, if it is given as f of x, capital X, so I'm just writing it as derivative of the function, small letter, f of x, then it implies, okay, then it implies that integration of this function, f of x, will be, integration of this function will be what? Antiderivative, so it's going to be f of x plus c. Now what is this c? From where does this c come? So this is called what? Integration of a function with respect to that particular variable. Alright, with respect to x will be f of x plus c. What is this? This c is actually called integration constant. Now what is this c? From where does this come? All of a sudden just jumping into here. How? I'll tell you about that also. See, integration actually is of two types. Okay, integration. Can I wrap this off now? Shall I? Okay. Integration is generally of two types. Alright, so I do not want to tell you about that in the beginning, so that do not want to confuse you. Now, of course, since we know up to some extent, okay, what is integration? Now, why do we use this integration? Integration actually are of two types, that is indefinite and definite. They are not very different, okay? Indefinite and definite. We have two types of integrations, that is definite integrals and indefinite. Definite integrals and indefinite integrals. Now, for example, very quickly again, for example, suppose indefinite integral will be, maybe you will be just given a graph and you will have to just find out the area where the limit is not given. But definite will be like, they will tell you exactly, okay, from 0 maybe up to this point, from 0 to a, find out the area under this curve. So that's like fixed. So that's what is the difference with definite and indefinite integrals. Now the problem was with C. Now, but I'll give you one example, another very nice example. That is, of course, this year hardly most of you went to the school because of the lockdown and this and that. But if you imagine your school, then every school, in every classroom, what happens is you have, a board, green boards or black boards or white boards. Generally, yeah, if we assume the blackboards, those olden days, the blackboards which was attached to the wall, painted black. Now, every classroom will have these blackboards, even whiteboards also, we can assume. Now, if I just tell you, find out the area. How will you find out the area of all the boards? Okay, blackboard, let me just say. Blackboards in your school. then definitely what I'll do there is, how am I supposed to find out the area of this board? That's quite simple, because the area of the board, what formula am I going to use? I'll be just using this. This is a rectangle in shape, isn't it? So I'm going to use this length into breadth. I'll find out the length, I'll find out the breadth, length into breadth multiply. I'm going to get the area of the blackboard or green board or whiteboard. Simple as that. But the question is, okay, that's one concept. Okay, now the question comes is, each and every classroom, will it have the same shape and size, same dimensions of blackboards in each and every classroom? Of course, that's why I prefer it to be like a blackboard, okay, because whiteboards generally come with fixed sizes. So most of the schools, they order that fixed particular size, so almost all the sizes may be same, so we may not be able to differentiate that much. But still, then whiteboards also, there are many shapes and sizes. So but if we consider those blackboards, so every classroom, what happens is, generally speaking is, every classroom, they have different shapes. I mean, not shapes, rectangular in shape only, but different sizes, different length. Some very big blackboards in their classroom, some in small rooms they have the smaller blackboards. So all the blackboards actually are like their dimensions are slightly different. Some are maybe very big because the classroom is very big. Some, maybe the blackboards are quite small, even though it's rectangular in shape. Maybe some, the blackboards are quite small because the room is small. But nevertheless, what do? Definitely we will be using the same formula, length into breadth, isn't it? Length into breadth only. Length into breadth only we will be using. But the areas are going to be different. Areas definitely are going to be different depending on the size of the blackboards. Now that concept you can associate with definite integrals. Okay, we will summarize that, but for now, that concept we can associate with the definite integrals. Just a common general term. Find out the area of the blackboards in your school. So we will be using the same formula, definitely length into breadth, but the areas of the blackboards of different classes, assuming that they have different shapes, different sizes, is going to be different. When you go to definite integrals, it's something like telling you, listen, go and find out the area of the blackboard of class, let's say class 12 science class, assuming that there is only one section. So that's very easy, because that one section will have just one board, no matter how big it is. So length maybe 10 meters, okay, whatever be that, no, let's say 5 meters. Breadth 3 meters, so length into breadth 5 into 3, 15 meters square. That's it, fixed. So that is associated with definite integral, where we have the dimensions fixed. But in both of these cases, what happens is we use the same formula. But here it was very definite, class 12 science, that particular section. Here indefinite in general as a whole, and that's the concept, and that is why we use this C, integration constant, in simple words. Okay, integration constant in definite integrals. We don't use that in indefinite integrals. We don't use that in definite integrals, because definite integrals, we already know the dimensions. What is its length? What is its breadth? So we will be fixing the length into breadth. We can put down the values: 5 meter, 3 meter, 5 into 3, 15 meters square. But indefinite, of course, it's just like a common. So it's just asking us a common formula. So what it tells us is, okay, integration, that is like area of the blackboard in the classroom. What are we going to do? We are going to use the formula length into breadth. It's something like telling us that we are going to use that formula length into breadth. But depending on the sizes of the blackboards, the value is going to be different. Some 15 meters square, some 20 meters square, some 30 meters square. So integration constant is something like that. I hope you've got my point, isn't it? So integration constant just tells us that, listen, we are going to be using the same formula everywhere only, but depending on the length and breadth or the dimensions, the definite value is going to be different. So that's why we use this integration constant. So definitely, I think you will have around about 7 exercises, 6 to 7 exercises, 5 to 6 exercises on indefinite integral. Then only we will be moving on to definite integrals, but they are not at all different. Okay, they are almost the same. We will be using the same formulas only, but the thing is,
Indefinite integrals will be you will be given the limits. You will be given the dimensions. Indefinite, no dimensions will be given. Just a general, just the formula there will be. So it's something like, which formula are you going to use to find out the area of the blackboard in your school? Something like that. Here, what is the area of the blackboard? Yeah, we can assume it's something like that. So that's why we use this integration constant. Okay, it's not a complicated figure which we really have to understand. No, it's a simple concept. All right, now. So that's what integration is all about. Okay, so now how do we name this? This is like integration. How do we name this? This is like integral of the function f of x with respect to x. Okay, integral of f of x with respect to x. And what is this f of x called? This is of course a function which is also called as integrand. Okay, this is also known as integrand, and x of course is that particular variable. So there are many more rules and regulations, many more things. So definitely all those we will be discussing in the next video onwards. So next video, of course, I will be definitely giving you another concept on this definite and indefinite integrals also. Okay, since we've started that, let me just quickly do that. Okay, one basic formula on integration. The first basic formula, I will be definitely doing this again in the next video also, because that's where we will be starting. But just a quick summary of what is the difference with definite and indefinite integrals. That is, see, this common formula that we have, x power n with respect to x. What was the derivative of x power n with respect to x? It was n into x power n minus 1. Isn't it? Here, of course, I'm not going to be explaining the formula. I just want to show you the difference between definite and indefinite integrals, but we'll be definitely doing a lot more about that in the coming videos. Now for x power n, integration of x power n with respect to x, we will be using this n plus 1 upon n plus 1 plus c, if it is definite, indefinite integration. Okay, indefinite integrals. Now for example, let's say x squared with respect to x. So here what happens is, see, this is indefinite, so no limits will be given to us. Okay, no limits. This is just the common formula that they are asking. So that's going to be what? x2 plus 1, that's 3. 2 plus 1, that's 3, because n is 2, so 2 plus 1, 3, 2 plus 1, 3, plus c. That's called indefinite integral. Alright, don't worry, as I say, we are going to be doing again in the coming exercise also. Just giving you a simple difference in the concept. But when it comes to, you got this, no? But when it comes to definite integral, what they will tell you is, they will tell you the limits also. That means they will tell you, okay, the curve is from 0, or maybe something like the curve, whatever, maybe this is the curve. What they will tell you is, the curve is, find out the area of the curve, under the curve, where the limits is like, let's say 1, 2, 3. They want you to find out only this area, this part only, along from 1 to 3 only, the limit. So that's what they will give you, 1 to 3, that is the limits, lower limit and upper limit. And what we will do here is, we will then remove the value of c, and we'll put down the values of 1 and 3. And again, I request you, please don't worry, I will be discussing this again. Now I'm just trying to give you the difference, okay, between definite and indefinite integrals. We will be doing a lot more about this, much more in details. But about that blackboard area, no, definite integral, indefinite, why we use c, what is the general formula, no, all that only. So there what we do is, we substitute the value of the upper limit in the variable minus the lower limit. That is like 3 cubed by 3, this is a constant, minus, next is 1 cubed by 3. So that means we will substitute the value of the upper limit and the lower limit one by one in the respective value that we get, and subtract it. So that's going to be 3 square minus 1 by 3. So that's like 9 minus 1 by 3, that's, isn't it? Because 3 square, because 3 square, that's simple. So that's going to be 27 minus 1, 26 by 3. So that was the difference, because in indefinite integral we got only x cubed by 3 plus c. That only gives us a value, not the formula that we will be using. But when you go for definite integral, where the limit will be given to you from there to there, what happens is, when we calculate, we get one unique value. That is, we get the value here, 26 by 3. So that's the only difference, okay? And that's why we use this integration constant in indefinite integrals. So don't be very tensed or serious about this
integration constant. It will be removed very soon when we start doing definite integration. Alright, so that's what it is, integration. So next video onwards we'll be starting with the mathematical part of integration, starting from the basic formulas, but for that, of course, I do request you to go to the derivative formulas, the concept. I'll be providing you the link below for if you haven't gone through the derivatives, concept of derivatives, the formulas and all. So please go through that also, because you really need to be prepared well enough to be ready to do integration. First derivative, differentiation, after that only you should come to integration. So I hope you will be ready when we meet the next time. Alright, okay, so all the best, study well, see you very soon. Bye bye.